so when we got the agenda, Tony and I both noticed that I was scheduled to speak first, and Tony was kind enough to send me an outline of everything that he was going to present, and he's done an amazing job of covering that material, and it was clear to both of us that it would work better if he came first. So I'll be building off of a few points that Tony left to build off of, and in particular I'm focusing my talk on the use of high magnetic fields. It's a bit of a career risk for me that I always have to talk about high magnetic fields, and I'll be focusing on evidence for quantum phase transition at a particular doping. So it's a different question than one you're asking, but is there evidence, first of all, that it's zero temperature phase transition? And then second of all, is there evidence of quantum critical behavior in that same vicinity, and namely under the superconducting dome, where we're using the magnetic fields to suppress the superconductivity as best we can. And even with the highest fields of now 90 Tesla and above, we can only suppress the superconducting dome to zero temperature in the least competent of the COOP rates, as well as the Nick-tide superconductors. But YBCO, we can only suppress down to about 50 Kelvin. Just one slide advertising the laboratory. We welcome users from around the world. In 2018 alone, we hosted experiments for over 2,000 users, 162 institutions across the United States, and if you include the entire world, 321 institutions from throughout the world. And there are fine pulse magnetic field laboratories at Los Alamos. These red lines are folks who came to Los Alamos. There are other pulse magnet labs in Dresden and in Toulouse. I'll show some data from Toulouse, as well as in Wuhan in China, and several laboratories in Japan. And for DC magnet labs, there are two branches at our laboratory, one in Tallahassee, these purple lines, and the other in Gainesville at the University of Florida. And there are also fine DC magnet laboratories in Nijmegen in the Netherlands, in Grenoble in France, in Hefei in China, and in Tsukuba in Japan. And to give you a sense of the size of the community, every year about 225 postdocs get data at the Magnet Lab, 560 graduate students. We publish in physics journals, coffee table journals, all sorts of places. But this is the statistic about which we're particularly proud. Every year, about 1/4 of our principal investigators, the people who are running the experiment, are first-time ever PIs. So if you have a need for high magnetic fields, we know how to make your experiment successful, even if you don't have experience. It's not a closed club. So I want to give just a few slides on technology, because even as we're struggling to understand why high-temperature superconductivity exists at all, there are hundreds and thousands of engineers that are turning it into a technology. And magnetic field for superconducting magnets versus year is undergoing its third revolution. The first was with the development of niobium titanium. This is still the only conductor used for magnetic resonance imaging around the world, as well as accelerator magnets. Both of those technologies are now starting to design and build magnets using niobium-3 tin. That's the second revolution, and NMR has done up to 24.6 Tesla. And now HTS is starting with its advance. And we've got a 32 Tesla, all superconducting magnet at the Magnet Lab. Well, it seems to have frozen up. There we go. And just this year, just a few months ago in Nature, there was an article where we achieved a test coil, proof of principle, of 45.5 Tesla with a small coil inside one of our resistive magnets. So 31 Tesla was from a resistive magnet, but the insert coil, which was this size, they only give me the nylon version as the manager, this size of coil generated 14.5 Tesla in the bore, inside a 31 Tesla magnetic field. So the world will change. We need to figure out quench protection, we need to figure out the stresses, and a number of other problems, but there will be very high field superconducting magnets in the coming decade or so. We're currently working on a 40 Tesla magnet, and I'll go to manual mode here. And in just the simplest schematic, if you plot critical current density, so not temperature, but critical current density on a log scale, and applied magnetic field, the ability for a superconductor to carry current dies out at some point due to the upper critical magnetic field. And the physics of that can be two mechanisms. One, as I show here schematically, you can spin polarize the magnetic field, the so-called Klogston limit, or a magnetic flux quantum can thread the coherence area. So for high TCs, you've got a very short coherence length, so a small coherence area, and it takes a huge magnetic field to kill the superconductivity. But notice niobium-3 tin is losing its entire ability to carry critical current, a supercurrent, at about 25 Tesla. And so for that reason, I make the assertion there will never be a niobium-3 tin magnet that exceeds 25 Tesla. And the reason is that this barrier is fundamental. It comes from on high, and it's given by the parameters of the superconductor itself. So how do low TCs compare to high TCs? This is critical current density for YBCO tape. It's anisotropic. It has two orientations. If the field is in the plane, then you get a very high critical current density. If it's perpendicular, it's lower. But notice that these are practically horizontal lines. And so the upper critical magnetic field doesn't play a role. It's somewhere over by the wall there. In fact, we've done experiments to 100 Tesla. We've not been able to suppress superconductivity in optimally doped YBCO. And the reason is that the reason that we're excited in particular is that the value of the critical current density is governed by engineers. So they've crystallographically aligned films of gadolinium-doped YBCO. Basically, the tape that we're using in these magnets is single crystal by the kilometer. It's polycrystalline, but they're aligned within a few degrees. They dope with zirconium because barium zirconate makes nanorods of normal state. And that pins the vortices in those small nanorods of normal state. So if we take Harold Hess's image of a single vortex and we make a perfect lattice out of it through the use of fake news, and then if you happen to have nanorods, I put them in exactly a hexagonal array. Of course, that's not the way nature works, but these vortices will preferentially find where you've got a nanorod and not move. And the point is that if your vortices move, you get dissipation. And so the superconductivity goes away unless you're pinning the vortices. Well, that is not given by the painting on the ceiling of Sistine Chapel. That is given by the creativity of engineers. And so they find unique new ways to screw in light bulbs as well as to pin dislocations. And so now there are 3 conductors that are being investigated for use in very high field magnets. So that's the reason we're excited about high magnetic fields being generated using high TC. And now I'll switch to the bulk of my talk on the physics. I'll give a quick introduction to high temperature superconductivity that's even older than the one that we got in the last talk, going back to the first year or two of high TC. But I'll spend most of my time, as I said, on phenomena evidencing a quantum phase transition near optimum doping. I'll focus on data in the whole doped cuprates, LSCO and BSLCO. There's other work by Rick Green's group in Maryland on electron dope I don't think I'll have time to go into. And then I'll focus on phenomena that suggest quantum criticality near that quantum phase transition. I'll mention the linear T resistivity, although that was covered quite well in the previous talk. There's recent reports of linear in magnetic field magnetoresistance. So absence of any scale in magnetic field in the low temperature limit in both the pnictides from James Analidis' group and in LSCO from our group. And then I'll present some evidence of quasi-particle mass divergence from quantum oscillations in cuprates from Brad Ramshaw, from barium-122 pnictide, Ian Fisher's group. And there's other evidence of logarithmic increase in specific heat, neodymium-doped LSCO. And I'll finish the talk on specific heat divergence in the low temperature limit of barium-122. Now, I'm running back and forth, hopping back and forth between cuprates, a number of different cuprates, YBCO in some cases, LSCO and others, BISCO and others, and the pnictide. But the reason is that the phenomenology is quite similar in these different materials. And the fact that they all exhibit high temperature superconductivity means that either nature is giving us a clue or nature is incredibly cruel. And we cannot rule that out. The common denominator of these three materials that I'll feature in this talk, they all have two-dimensional square lattices of some transition metal, either copper or iron. The layers are separated by barium, yttrium, lanthanum, and or strontium. And so you've got these 2D or somewhat buckled 2D layers of your transition metal in a square lattice. So, before there was control of doping, before there was a phase diagram, back in 1988, this is Horst Stormer's only foray into high TC, and then he got the hell out of it. Just further proof of how bright he is as a scientist. But in this paper, he links ideal linear T to the highest TC samples. So they didn't realize that they were changing doping necessarily. They had no control over doping, but they were characterizing the quality of the samples by the sharpness of the transition. And in organizing the samples like this, the narrowest transition, which was also the highest TC, had a linear resistivity that extrapolated back to the origin. And still today, that's sort of the signature of the best behavior of a cuprate. Whether that's the right physical interpretation or not isn't clear. But as you get to, and as you saw in the previous talk, and you'll see in this talk, there are many materials for which the slope is linear, but the intercept is finite. And we still have this prejudice, perhaps, that the ideal behavior is when the intercept is 0. And I'll point out that we've now achieved that. Ivan Bozovich's group, in particular, has achieved that in LSCO thin films formed by MBE. So similar results were found in LSCO. This is like data that Tony Carrington showed. This comes from Hide Takagi and Bertram Batlog's work from '92. This is LSCO. Here they can control the doping with strontium concentration. Once they were able to make single crystals, they could then do the systematic behavior of transport, and you get the best linear behavior at optimum doping here at 0.18, 0.17, I think, but I didn't see it labeled. And you see the finite extrapolation for this material that's somewhat dirtier than YBCO. So this is now the state of the art on lanthanum strontium copper oxide at 0.19, linear temperature dependence, and the intercept is very close to 0, certainly within our ability to extrapolate. Why should optimal linearity of the normal state resistivity to 800 Kelvin in the VSCO data from Sam Martin that Tony showed in his talk, all the way down to TC, it's not clear even to this day. But the resistivity, as Tony discussed in his talk, it seems to know nothing about electron-electron scattering, which would go as T squared. Electron-phonon scattering would have a linear temperature behavior over some range, but then would deviate from it. Thermal expansion of the lattice doesn't seem to play a role. And even the unitary scattering limit, where the electrons would have a mean free path that gets shorter and shorter as the resistivity goes up, eventually that mean free path gets to the point where it's the distance between atoms. So for any resistivities higher than this, and it keeps going up, your electron, if it exists as a quasiparticle, is scattering more frequently than off of every atom that it passes. And so this has at least meant to some that it implies to some that the electrons create a viscous quantum fluid, as Tony mentioned, and then quickly moved on, which is the same strategy that I will adopt, to quickly mention but then move on. The electrons in these pictures that are based on physics of black holes and Planckian dissipation is that the electrons lose their identity as particles, and you have a fully entangled quantum mechanical state. Sir?
But a viscous Fermi liquid goes in the opposite direction with temperature. It becomes more viscous at room.
Yes. But their claim, which I would not be able to defend in the least, is that the dissipation goes as kDT in this picture, and that's limited by this maximum dissipation allowable in a quantum mechanical system. Okay. Right. How did I do? This was already shown by Tony, so I'll just point out that the YBCO phase diagram in 2001, all of these measurements were taken at high temperatures. So even the data points that are down low on this plot were taken from, for example, heat capacity up at TC. And so our philosophy will be to then suppress the superconducting dome to actually measure physical properties in this low temperature limit. So the YBCO phase diagram is complicated. I'll come back to this later because in connection with some quantum oscillation data from Brad Ramshaw, even though we're focusing on whatever might be happening near optimum doping, there's some evidence that there's also mass divergence, not just at here, but also there. But most of my talk will be focused right here near optimum doping. So a quantum critical point, and this goes to some of the discussion that's been indicated here, it exists at a single value of a tuning parameter. This can be doping, as it is in the cuprates and the pnictides. It can be pressure, as it is in the heavy fermions. It can be any thermodynamic tuning parameter. And there's a quantum phase transition, a zero temperature phase transition. And then on top of that, in this region that's shaded pink here, you get anomalously slow dynamics, quasi-particle mass enhancement. You get scale invariance, which would be power law behaviors. And perhaps the linear in T is a quantum critical behavior. It initially was thought to be insane to talk about quantum criticality up to 800 Kelvin. But I think it's an active discussion now. You know, the critical regime around phase transitions, for thermally driven phase transitions, is often just a few parts in 100 or a few parts in 1,000 of the region around TC. And this would postulate a huge regime of critical behavior. I'm not going to vote. Yeah, 5 minutes to go?
No.
Oh.
So in your schematic of a quantum critical point, do you require that there's a broken symmetry on one side of the point?
I'm fine with that statement, yes. That there's a broken symmetry on one side.
Okay.
That's why there's a line on one side. The other is a crossover to what would be, Fermi liquid behavior. And I actually think that there is mounting evidence of a real phase transition at this pseudo gap transition here. So this is the simplified phase diagram for cuprates, whole doped cuprates with TCs from 40 to 150 Kelvin, the mercury compound under pressure, and they have this linear T resistivity that Tony presented. And here's the barium-122 compound that we'll be studying, where the magnetism actually comes out all the way over to optimum doping. And we know that we have a transition from spin density wave to a non-magnetic phase near optimum doping. And so we'll be looking for critical behavior in that regime. And as Tony mentioned, there are quite a few other physical systems that show this phenomenology of superconductivity seemingly stabilized near quantum phase transition, and no one really knows why. This is an example that was not in the zoo of compounds that Tony showed. These are the heavy fermions. So these are three-dimensional systems that have F electrons in them that give you a heavy mass. And this is work from Gil Lonsrich's group, where his tuning parameter is pressure. And he was noticing that the transition to antiferromagnetism was dropping with pressure, and he wanted to go to that point where the phase transition drops to zero, because we have a theory of phase transitions that are driven by temperature, but we don't really have a theory of phase transitions that are driven by variation of some parameter at zero temperature. So quantum fluctuations would presumably play a role. So he's asking nature, do you want to be a magnet or a non-magnet? And nature, right where it has the decision to make it zero temperature, decides, like a 4-year-old, it doesn't want to be either. It wants to be a superconductor. And often it's not, it's a superconductor. But there are examples out there where you'll get a ferroelectric phase right at this zero temperature phase transition. So it seems as though nature is able to explore its phase space at quantum phase transitions in order to find new phases to settle into that, at least prima facie, have little to do with the phase on either side, but surely there's some link, and that's what we're seeking. So I'll now go into the first high field data, and the physical result is the observation of a peak in the Hall number, a non-monotonic evolution of the Hall effect that evidences a quantum phase transition in whole-doped cuprates. So, as we saw earlier, you make a two-dimensional Hall structure, you apply a current down the spine, you either measure the longitudinal resistivity or the transverse resistivity. I'll use the same terminology. Our Hall is just the slope of the Hall voltage that is linear in H, and then in a single band metal, that's equal to 1 over NE, where N is the number of carriers. Well, when we measure the Hall coefficient at relatively high temperatures above 50 Kelvin for different strontium dopings, so we're going from here up to there, it's a monotonic behavior, and there's not anything that's particularly special there. What we've done is we've measured the Hall coefficient, plotted it here, and then we normalize the Hall number so it's carriers per copper. So it's sort of a logical way to interpret, and you'll notice that in the 0.08 sample, you've got 0.08 carriers measured per copper. And in fact, in some data that was in the previous talk, Yoichi Endo's group measured in this regime, and the Hall number is just tracking your doping perfectly. Well, here it's screaming up. And there was some discussion in the previous talk about whether we're going from P to 1 plus P. And in fact, at least in LSCO, what I think is happening, because we measure this all the way up to 2 apparent electrons per copper, I think this is just screaming up to be a positive divergence to infinity, because you're going to cross over from hole doped to electron doped, or hole behavior to electron behavior, as you go through the band filling and the curvature of your band changes. And we know, at least in LSCO, that this occurs at around 0.28 or so. And so that's another complication to this whole discussion of whether the systems go from P to 1 plus P. We know that there's going to be a divergence to positive infinity as you go into the overdope regime, because eventually your band curvature changes. But the important part of this result comes when you use a high magnetic field to suppress the superconductivity. And then no longer is your Hall coefficient monotonic. Here at the 0.17 you see it crosses, and that's what gives you this non-monotonic behavior at low temperatures that you cannot see when the superconducting phase is in the way. Now, it's not just the one curve. We took many more curves. So here we've added, these are the same data, just plotted on different axes, but we've added the data at 0.165, at 0.175, and so you can see there's quite a few samples that show this non-monotonic behavior that gives rise to this peak. So a peak in the Hall number gives some evidence that there's something dramatic happening to the Fermi surface, some sort of phase transition occurring in the system right near optimum doping. In fact, TC, maximum TC, is sitting at right 0.17 in this sample. These are results from 2009. We actually first saw this effect in BISCO because it comes in platelet-like samples in 2003. Here it's much harder to know the exact doping because as you're pumping lanthanum in, you're clearly getting oxygen compensating, so you don't really know your doping. But the point here is that even if this is not the precise number, the maximum TC is once again just near this peak in the measured Hall number. And so we've seen this phenomenon in 2 systems. We've looked for it in others. In YBCO it's not seen by our group or the TIFAIR data because you can't suppress superconductivity below 50 Kelvin. And this peak doesn't show up until below 50 Kelvin. So we just don't have the answer in any materials other than LSCO and single layer BISCO. But this peak occurs near optimum TC in both of those sets of systems. Okay, so now if we've shown some evidence of a phase transition near optimum doping, and I'll cover as many of these as I can, evidencing quantum critical point near optimum doping, and I can make my talk available to folks because I don't know if I'll get to all of these. So, the linear and temperature resistivity is canonical to all of the cuprates and the pnictides, but the linear magnetoresistance came as quite a surprise. It's a new phenomenon. I'll show that it exists in a second system, but it was first reported in data up to 90 Tesla in an iron pnictide superconducting this barium iron arsenic doped with phosphorus. This is the one pnictide that I show in this talk, and here you can see at low temperatures, once 47 Tesla has suppressed the superconductivity, you get a linear in H magnetoresistance for the remaining dynamic range of your measurement. And they find in this system, in barium 122, that temperature and magnetic field effects add in quadrature, which is a rather interesting result. So the natural scale to convert temperature to energy is kBT, and for magnetic field it's mu naught h, or mu BH, and then they have these two parameters they call alpha and gamma, but they add these two in quadrature. So if you're in the high temperature limit, this term dominates, that becomes small, and so you get linear in T. If you're in the high field limit, this term dominates and you get linear in H. We actually see something different in the material that I'll be reporting on, LSCO. So this is work that just came out last year in Science. Paula Geraldo Gallo did an excellent job. She's now a professor back in Bogota, her hometown. And these are the data that I showed in the barium compound from James Analidis' group. And these are our data from LSCO thin films, the data that I showed you earlier, the temperature dependence, the linear temperature dependence that goes to the intercept. And you can see that this magnetoresistance is really quite linear as you get to the high field regime. So this is rho versus T, also quite linear as I showed before. And these are the rho versus H data. These are the same as these, just enlarged so you can see better. We define our slope with temperature as alpha and our slope with field as beta. And in particular, one of the phenomena that Yoichi and I saw decades ago but never really remarked on, but is really quite clear in this system, is that you get dead linear almost down to zero field right near TC in zero field. There's a little bit of superconducting fluctuation there, and we do know that it's by symmetry, you've got to have some B squared component, but it really does seem to shrink to almost nothing, and you get this linear behavior, in this case from just a few Tesla all the way up to 80 Tesla. So we plot that value of beta, and we discover that we can get into a low temperature regime. So at 40 Kelvin at TC, the linear slope is really quite large. As you go up to higher and higher temperatures, eventually it's B squared over the entire range. But below about 30 Kelvin, you saturate so that your linear regime, as it's shrinking because you're running out of magnetic field, does seem to have achieved some low temperature value. And so we'll be focusing on that value. And here's the key result. In LSCO, we see linear in H above 50 Tesla. And if we plot the values at 80 Tesla here in blue, 70 Tesla in light blue, 60, 50, you'll notice that over this regime below 50 Kelvin, we've got not only linear in H, but we've got linear in T. So we've got linearity in both of these values, and so it's as if our scaling goes as something like T plus B. And that is in striking qualitative inconsistency with the quadrature behavior seen in barium 122. It's clearly observed in that system. It's an experimental fact. We don't know why it's different. But with this kind of adding in quadrature, you will never get a regime where you're linear in both B and T. And we clearly see that here. Okay, so then the question is, how does that linear coefficient change as a function of angle? And Arkady Schechter is working on a manuscript where he rotates the sample. As you put the field more and more in the plane, you run out of field more readily, but you're plotting this slope as a function of orientation of the magnetic field from along the c-axis to in the plane. And what he finds in this plot of the slope beta versus theta, the degree, here when you're perpendicular to the planes, you've got a maximum value for the linear in H coefficient, and then that value of that coefficient follows a magnitude of cosine theta over quite a range of theta. So the slope of the linear magnetoresistance tracks cosine theta, absolute value, indicating there's some sort of planar physics. It's not arising from spin interactions with the magnetic field. So two more things to cover. Several observations of quasi-particle mass divergence near optimum doping, and specific heat divergence in the low temperature limit in the Nick-tide. So we remark that linear in H resistivity is evidence of quantum criticality, really don't have an idea why it's evidence of criticality. It's simply a power law behavior that's unexpected. It's linear in the thermodynamic quantity, just as resistivity is linear in temperature. So there's similarities, but I don't think there's anybody who's got a theoretical understanding for what's causing this linear in H that's seen in both the nuclides and the cuprates, but I see someone who seems to be voluntary.
No, what causes linear in T?
Say again?
What causes linear in T?
Exactly. That's why if we're willing to talk about the one thing we don't know about, let's be honest and talk about all the other things we don't know about. But the engineers are still making something out of this mess. So, all right. So these are data from Brad Ramshaw in YBCO using high magnetic fields to evidence quantum criticality near optimum doping in a high temperature superconductor, and I'll spend some time on quantum oscillations. So this is the regime in the phase diagram. This is the superconducting dome for YBCO, where the quantum oscillations were first observed. And the reason is that you can make a highly ordered state. I can't make a highly ordered state. These geniuses from University of British Columbia can make a highly ordered state where the chains are half occupied with oxygen. Every other chain is empty, and the remaining chains are half occupied. So it's a very ordered state, and so they get very clean metallic behavior, and you see quantum oscillations. As you move in this direction, Brad Ramshaw realized you're getting close to 07, which is another stoichiometric point where you should have high degrees of order. And so they changed the entire philosophy. Rather than annealing the samples to get the oxygen to order, they realized that the best thing to do here is you've only got a few point defects, so quench cool the samples so the oxygen just freezes out rather than puddling up. So that allowed them, for the first time, to be able to see quantum oscillations. I'm sure you can all see them here in the data. I'm only poking fun at Brad because he's a good friend. This is incredibly good data. And they just subtract a smooth background, and you see very clear oscillations in each of these three data sets for three different dopings. And they measure the temperature dependence. It's largest at low temperatures, smallest at high temperatures, from 1 to 7 Kelvin. And from that, they can deduce a mass of the quasiparticles for that doping. So one of the mantras here is clearly we need bigger magnets. That's, if any of you have $20 to $50 million, see me. I've got a business card with an address on it. But when they measure the temperature dependence of those quantum oscillations, the speed with which they decay gives you direct information on the mass of the quasiparticles. And this is a single pocket system, so it's a very simple analysis. And this mass goes from sort of 1.3 up to about 3.7 over a very limited range of doping.
Greg, is it a single pocket system?
There's the bilayer system. You showed the two pockets due to bilayer coupling, and I'm not going to get into it. Brad certainly analyzes the data like it's a single pocket system. I have his phone number if you don't. And so then he plots 1 over the mass, and you're tempted, as a human being, to make a linear extrapolation, and lo and behold, the mass, 1 over the mass would go to 0, the mass would go to infinity, right near optimum doping. Earlier data, and this is the same group with a few changes in the junior members, but data by Sushi Sebastian headed up, she's a co-author on the Brad Ramshaw paper as well, was in this regime, the first samples that showed quantum oscillations, and they seem to show a mass divergence down at 0.08. So at both ends of that phase diagram, I'll show you again, there's evidence of mass divergence. But I'm mostly interested in the optimum doping. And the other thing to point out, as I pointed out earlier, 80 Tesla, you still cannot suppress the superconductivity below about 35 Kelvin. And this is the zero resistance state. So the transition takes you even higher. This whole area gets obscured because of the robustness of the superconductivity. And even 100 Tesla doesn't suppress it much more than that. So we need bigger magnets. So this is the phase diagram I showed you, and lo and behold, these are the 2 points that show a mass divergence in YBCO, where you've got the ends of this charge density wave ordered state. Okay, so for the final part of my talk, the biggest section of my talk is reporting on specific heat divergence in the low temperature limit in barium-122 Nictide. So we'll turn to this material because it has a lower upper critical magnetic field than YBCO. We want to do specific heat, which you cannot do in a pulse magnet, so we're limited to DC magnets. And in fact, to get the signal to noise we needed, we were limited to our 35 Tesla magnets. But it does give you thermodynamic evidence of a quasi-particle mass divergence at optimum doping. So as Tony showed in his talk, the barium-122 compounds have 4 pockets, 2 at the gamma point, 2 out at the corners of the Brouillon zone. And the isovalent phosphorus substitution maps out a familiar looking phase diagram with the spin density wave phase that's crashing to 0 right where TC is optimum. And I don't want people who don't have the decades of perspective to lose point of the fact when it was first seen that so many systems had magnetism crashing down at the top of a superconducting dome. This was a sea change. This is the only logical way to find a new superconductor. Find a magnetic system, tune some parameter, thermodynamic parameter like doping or pressure. If the magnetic phase transition is dropping, go to the point where it goes to 0, and you're likely as not to see superconductivity. The only other way to find superconductors is to put several elements into a mortar and pestle, grind them up, bake them, and then put contacts on and measure. And that's the way superconductors were discovered until this phenomenology was discovered, and we still have little idea as to what's going on here. Why is nature giving us a predictable way to find superconductivity? Yeah.
But there's no magnetic transition at the equivalent point in the cuprates.
That's right. And the cuprates have a higher TC. But there does seem to be some sort of phase transition.
Yes.
We just don't know what it is.
Yes.
So this can be ferromagnetism, in which case sometimes a superconducting dome is nestled only on the left side. It's more often spin density wave or anti-ferromagnetism, and you get a symmetric superconducting dome. There are examples, as I mentioned, where this is a ferroelectric system. We don't really understand what's going on here. I think there was a question over here. Okay. So this has the non-Fermi liquid exhibiting linear and T resistivity, and the question is there a quantum critical point near optimum doping? Well, the first evidence of mass enhancement comes from work by Tony Carrington. He's fitting the jump at C over T at TC. So these are zero field measurements, C over T, after subtracting out the normal state. So this would be the normal state up above TC, and it's just 0 on this plot, so that he can then give us in millijoules per mole Kelvin squared the size of this jump at TC. This is the reference for that work. Phil was your grad student at the time? And so they're measuring on back of this phonon background this jump at TC, and they remove this normal state specific heat in order to do this analysis. And what they find is a dramatic increase, as you can see, going from 0.38 phosphorus doping to 0.30. This jump is almost doubling. Here from 0.38 to 0.30. 30 is the optimum TC. You see this huge enhancement in the jump at TC. And that's evidence of a mass enhancement. But it's a little bit harder to analyze. It's a many band system. But clearly there's a divergence. They fit it to a logarithmic divergence, as you would expect from a magnetic phase transition. And then in high magnetic fields, they take the same system, they measure quantum oscillations in magnetization at the Magnet Lab in Toulouse, and these quantum oscillations arise from the formation of lambda levels. They fit to the standard formula, which is a transform of the Fermi-Dirac statistics. If you'd like to learn about quantum oscillations, this is the Bible still, Schoenberg, 1984, magnetic oscillations in metals. But this temperature dependence of the amplitude of the oscillations as a function of different dopings here gives them the mass from quantum oscillations from the one pocket that's showing the quantum oscillations. So here they've got the resolution to nail down the mass divergence from a single pocket. And they see this clear enhancement in the mass as you approach 0.3. And they're taking this data up to 60 Tesla because you can do quantum oscillations in a pulse magnet. So what Camilla and the rest of my group was working on was specific heat in this system. And these are data from James Analytis just to illustrate that for the higher TC system, 29 Kelvin near optimum doping, we cannot go down to arbitrarily low temperatures because our magnetic field is limited to 35 Tesla, so we're not able to measure any of this regime. And so, at least near optimum doping, we're stuck looking at a superconductor. We're not able to measure the specific heat of the normal state. But as you move to more overdoped samples over here, in this range, so for these 5 samples, up to that point, we're able to have enough of the normal state below 35 Tesla that we can measure the specific heat as we apply a magnetic field. And there's a reason that we want to do that. It becomes a relatively clear message that what we're measuring is the change in specific heat as you apply a magnetic field, and therefore you're measuring the recovery of density of states by suppressing the superconductivity. And so we're limited in the doping range, that's the negative thing, but we're measuring the total density of states from all of the bands put together that is recovered by suppressing the superconductivity. So as a function of temperature, we get the canonical behavior, this linear plot of C over T versus T squared. This would be the phonon term that gives you this finite slope. You can back extrapolate to 0 temperature. This gives you the Sommerfeld coefficient, which gives you information about either disorder in your system or mass of your carriers. But the point is that we don't worry about this offset because we're really interested in what is recovered as you apply the magnetic field. Well, these are the data you've seen several times now on the sample with phosphorus doping of 0.46. So we're looking at this sample in green. And we've got a very clear square root of H, which evidences nodes in the energy gap, and then we get a saturation once we're above HC2. If we take that same data and plot versus square root of H, you can see this very nice linear behavior on square root of H. There's some finite temperature effects because we're measuring at 1.5 Kelvin, and your gap's dropping to 0 here. So you've got some thermal excitations across the gap, but this is the region where you've got a superconducting phase. This is the region where you're in the normal state. And so we'll plot that value of gamma H as a function of doping. These are the 5 different dopings that we can measure. And this value of gamma H, from back extrapolating the linear behavior, the square root of H behavior, so this gamma H, which clearly has a strong doping dependence, is plotted here at these 5 dopings going from 0.6 to 0.44. You see that we're doubling roughly the value of gamma H. So we can convert these numbers of specific heat in a quasi-2-dimensional system by a very simple formula that has a prefactor out front that has the area of the Brillouin zone in it, and then a sum of the number of pockets of type I times the mass of those pockets. Well, in this case, you've got 4 different pockets, but you've only got 1 pocket of each one, so your n sub i's are always equal to 1, and so you're measuring the sum of the masses of these 4 pockets in converting your electronic specific heat to mass. So on one side of this plot, we're showing the gamma H, the recovered specific heat, and we're showing the total mass of the pockets engaged in superconductivity. And it's going from about 5.5 up to about 11.5 electron masses, just a few minutes. Yep. So if we take these data now, and instead of plotting in terms of mass, we plot as 1 over the sum of the masses, then the data, once again, much like Brad Ramshaw's quantum oscillation data in YBCO, seem to evidence a divergence of mass right at the optimum doping. So this mass divergence, the idea is that right at that phase transition at optimum doping, you've got a mass divergence. Now this ratio is doping dependent. If we compare to Phil Walmsley's data, which is on the beta pocket, with our data, which is presumably measuring all of the superconducting pockets, the ratio goes from 2.6 bigger to 4.3 bigger. And so the doping dependence is showing a stronger divergence as you approach optimum doping when you're looking at all the pockets. That might suggest that the pockets at the center of the Brillouin zone, quantum oscillations are measuring the beta pocket at the edge of the Brillouin zone. So perhaps the mass enhancement is going faster for the pockets near the center of the Brillouin zone. So those pockets are coupling more strongly to the quantum fluctuations in barium 122. And so just to summarize, mass divergence was first seen in quantum oscillations and specific heat jump in Tony Carrington's group at TC in the case of the specific heat jump, and then in the beta pocket in high field quantum transport measurements. We're doing specific heat measurements looking at all the pockets. We also see a mass divergence, and in this case the mass divergence also seems to occur right near optimum doping, as was reported by Tony Carrington's group. So for this quasi-2D system, this provides a thermodynamic measurement of the sum masses from all the superconducting pockets of the Fermi surface. The data extrapolate to a mass divergence near optimum doping, similar to previous reports from YBCO quantum oscillations, Brad Ramshaw. And so this has been the program of the talk, attempting to give a state-of-the-art survey as best we can of evidence for phase transitions near optimum doping. This is a big field, and we have less than an hour to present it. And also phenomena evidencing quantum critical point. And the general theme of this talk has been those experiments that require very high magnetic fields. I guess it's not on this slide, in order to get the data. Thank you very much.
Okay, questions? Andrew?
Greg, I don't want to make it as a comment, it's more like a question. You put several times that we don't understand why there is superconductivity near a magnetic quantum critical point. I think there's a number of papers from various groups which said two things. A is that magnetic fluctuations do promote superconductivity,
yes.
And they have a dome, and in case of ferromagnets, the dome is asymmetric and more on the ordered side.
Yes.
And on the other hand, the effective mass diverges at the critical point. What we don't understand, of course, is linear resistivity.
Right.
But we do understand mass divergence, and we do understand that superconductivity form a dome near the critical point.
When there's a magnetic phase nearby.
Yes, when there is
Right.
a magnetic
That's
phase
a good
nearby.
point. Yes,
Yes.
thank you. And would you agree with Seamus that in the cuprates, we don't appear to have magnetism nearby? So there's something else going on in the ones that are working best, except of course for the hydrides under insane pressures.
Uji?
Okay, you mentioned the similarity between YBCO and the barium 122. Because at the quantum critical point, mass diverging behavior.
Yes.
But the main differences are in barium 122, penetration depth shows the diverging behavior at QCP. But in YBCO, no evidence of the diverging penetration depth.
In YBCO, no evidence of
no
the
evidence of
diverging-
the diverging penetration depth. Penetration depth
Penetration depth.
Oh, okay.
as a QCP. That's the main difference.
Okay. Point well taken.
You were emphasizing the mass divergence from the jump in the specific heat as well as from your T equals 0 gamma and the high field state. I was wondering, if you take the ratio of those two, right, is the sort of the strength of the superconductivity staying constant actually? So, I mean, the size of the jump could be also changing because you're going in a strong coupling regime, right? It's sort of, so,
Right.
So if you took the ratio between those two, is that a constant?
So we're out at high enough dopings. We're going to need to retape the wire here. I tripped over it several times, so it's now basically untaped. I don't know if I have time to go. I think I have time to track it down. If we look, for example, here, our data are way out here. So we're at about 0.44 up. They sort of agree, but our data tend to agree here and be a little bit lower there for reasons I don't understand. I don't know if you have a comment whether this would be due to strong coupling turning on or not.
Well, the The assumption in the analysis is that it's not strong coupling, and the main reason for that is that you see that TC doesn't change actually over that range of doping.
And you link it to superfluid density, as I recall.
So, well, no, so the interpretation of that jump is exactly in mass divergence.
Right.
That's it.
George?
In the regime where you see the T plus H behavior, and you pointed out that it was rather an orbital effect than a spin effect.
Yes.
Is it conceivable to do magnetization measurements in this system?
It's
I want to have a thermodynamic variable.
right. It's not inconceivable. Absolute magnetization measurements are not easy to make in pulsed magnets, and we need to be doing it in pulsed magnets. But I could ask some of the folks who are more expert. Neil Harrison, if you know Neil, would be a very good person to ask whether he thought he could get good magnetization data. You're not looking for oscillations. You're looking for absolute magnetization. That's a much
I
more
want to see the
difficult.
scaling behavior that you find, which is
Right.
incredibly beautiful, surprising and not understood in any way in a thermodynamic object that
Yes.
is remotely understandable. I mean,
Right. That's you asked for something that makes sense from a theoretical point of view. It may make sense from an experimental, but let's try to remember to ask Neil Harrison. Yeah.
All right, Tony.
Greg, switching back to the cuprates, you emphasise that there's an increase in the heat, in the mass, 2 points in the dome.
Yes.
And, so for one near optimal doping, there's, if you wish to interpret in terms of coupling to critical fluctuations, there's two possible orders you're coupling to. It's pseudo-gap or the CDW.
Right.
But on the one on the left, right, the only game in town is the CDW, right?
Yes.
So isn't it then logical to say that the thing which is giving you mass enhancement on both of these is indeed the CDW, and that neither of them have got anything to do with high temperature superconductivity?
I think that that's a defendable position to take. I would say that there's not a lot in the cuprates that is amenable to logic, so I don't know that that's the strength of your argument. But certainly given that here there's a mass divergence that looks identical in the phenomenology of the experiment to what we see there, we meaning the groups that reported it, not myself. I would have no objection to linking the two, but as you pointed out at the start of your statement, there's other things that come crashing down right here.
Yeah, on that side, but not on the other.
Exactly.
So can I ask you two guys the same question, perhaps to help some of the students?
He answers first.
Well, okay. You both are extremely persuasive that there is some exotic critical point somewhere near point 2 in two different classes of materials with very exotic transport properties. Just beautiful. But for a quantum critical explanation for all those phenomena, you have to have a symmetry breaking at or near that point.
Right.
So either A, it doesn't matter which symmetry is broken, any symmetry breaking will do in order to produce linear T resistivity and high TC superconductivity, or B, we need to know which is the critical one. So let me ask Tony first. Would you be willing to volunteer which broken symmetry we're supposed to be looking for?
I say it's A. So I'll leave you if you want to defend B and then choose the symmetry.
I agree that linear resistivity is a problem, but my view is that there isn't a quantum critical point in the optimal doping. My view is there's a quantum critical point at the end of the antiferromagnetic phase.
I understand. And you have the same view for iron-based superconductors.
In iron-based, it's not so clear-cut because the difference between those 2 points is not so small. It's quite small.
but we don't need to have a symmetry breaking necessarily to have a quantum critical one.
But that's excellent.
Then you need something more exotic.
But
Yes, exactly. Okay, so
And to me, the most obvious phenomenology of the cuprates the linear in T, and then all these other phenomena that are occurring near optimum doping, suggests to me that we don't need to be looking for, in particular, what symmetry is being broken.
Any symmetry will do.
Well, no, I think there's something more exotic going on.
Okay.
Could you put back that graph you had? Because I wanted to make a comment.
And that graph I had.
This picture you had.
Well done, Greg.
So I wanted to make a comment which connects to what Tony's question was and what Yuji's question was. You find a mass divergence at PC1 and a mass divergence at PC2.
Right.
And both of those are found in high magnetic fields.
Yes.
But if you look at low magnetic fields at the magnetic penetration depth as you cross across this, nothing happens either at PC1 or at PC2
That's right.
in any of the hundreds of measurements that are
Yeah, so most recently I think Ivan Bozovic and his LSCO samples, it's just cruising and it goes to zero here.
So he sees some quantum critical scaling at that other PC max.
Yes.
And Lemberger and the UBC group saw it if you would just move down at the lowest one, which is the PC min. But nothing in the penetration depth at either PC1 or PC2.
Right. I don't understand.
Is your just for clarity, is your argument that the state that exists at very high fields and cuprates is different than the state from which the high TC superconductor?
I'm just stating experimental facts.
Okay, good.
I hope not, but I don't know how convincing my argument would be.
With the understanding that my memory may betray me, but I think there is old-legged result that if you have one band superconductor and you ask which mass goes into penetration depth, bare one or renormalized one, it's a bare one, not renormalized one. So in this respect, it's important that you have two bands. It's not, this doesn't happen in two-band superconductors, and this was in iron-based system. Everything is fine. There is one-to-one
restate, in a
correspondence.
single-band system, it's the bare mass.
Bare mass.
I
Yeah.
think that's true only if you have Galilean and Baire.
Probably, yes.
Yeah, so it's not relevant.
But
So last question here, please.
What does, in your opinion, have to say voltage switches in both points?
Oh, wow. I have no idea. These 2 points are defined by the charge density wave. I'm not aware of anything special happening in the vortex physics.
Well, since we're talking about the potentialities, also in the variable system, I don't know if there's something in there.
And neither do I.
All right,
Sorry.
on that
On that-
hopeful note,
Yes, sorry.
let us finish this.
Underscoring my ignorance, we'll end there.
Thank the speakers.